transformer, space-time in physics in the ancient history. The content of the first talk. Thinkers lead Aristotle, Pythagoras, Archimedes, Heraclit. The context, the description and calculation happened in the Euclidean vector space.
When I explain this exercise, so the exercise I want to explain first is the idea about to explore the space with vectors.
Oh.
Maybe you start very simple and become more dancey later.
But I move my hands first, no?
Yes. But how do I go back? Is it like this? You can do this or you can do this. Yeah, maybe backwards is not possible for the human body.
So you can, for instance, start to put both hands on your stomach and just feel how the hands, where they are attached. And then you can start to lengthen the fingers towards the front. And this means that your vector will, one moment, grow. Shit, I lost the game. Fuck.
Everybody finds their own direction. Let's search for our own direction.
So if you maybe this and this, you still go straight. I cannot move. But here I move, because this is longer.
Maybe we do some vector mathematics so that it gets clearer.
It's like this.
Still have a component in this direction, so you go somewhere like that.
Taking the energy out, releasing everything else that we don't do. What do we need to do? That we don't compromise the gathering of the energy, but we also don't go diagonally down. How much energy, how much distance, we suck it a bit. Forward.
It goes down and up, no?
Somehow it goes down and up.
With the finger, with the little finger.
Ah, you feel it in the little finger.
Yeah, when I go here, and then the little finger has to come.
Yes, the little finger
from
has to
there
catch
to
it.
there.
There is logic for it. You could have little fingers like that, and then you have a problem.
It's useful to have some fat.
Actually, absolutely pull yourself. The thing with a t-shirt. Let's do a t-shirt. Again, another t-shirt pull. Be fine.
So the longer the vector is, the faster you are, and of course you move into the direction as the vector has a direction and a length, which means a strength somehow. Yeah, good luck, play with this.
Good luck, play with this.
Imagine this exercise lasts for 1,000 years.
faster.
There were always haircuts.
This was how physics and mathematics was made. Next, you come to the classical time of science and the concepts of space. This is the time of the Renaissance. It is from the medieval to around 1700. And the models used in this time was still the 3D space-time and gravitational forces and mass points. Thinkers in this time, Newton, Kepler, Copernicus, Galileo, because of him, physics became an independent science. Before it was part of philosophy. Descartes spoke against the ancient description of the world. Newton mechanics and mathematical tools like machine. Now it was possible to calculate the complex movement of the stars and planets. Now we come to the next exercise in which you are mass points.
Mass points, so like exosyllables, this is the point of mass and this.
No.
This is an object somewhere in space. It is not moving at all, it needs a force to move. When I give the force like this, it starts to move in a straight line.
Your whole body, mathematics is still quite simple. It's too complicated to describe your whole body. And that's why I think that you will tiny little ball this size. You just don't.
This is a heavily object in the center.
You are not.
One of the small object, when it has no velocity, it would just fall onto the other object. This is how gravity works. I give a bit of force that it normally wants to move in a straight line, but because of this, the trajectory will be a little bit bad.
One of these is the not moving center of the gravity, and the other one can start to slowly move in an ellipse around the center of the gravity.
We don't crash into the center of the gravity.
Perfect orbit of planets, which is the ellipse region.
It is like somebody's pulling. The weaker force is, the more it becomes influenced by the gravitating object in the center. When the right amount of force at the beginning, then it will travel around in an ellipse. Actually, it wants to fall on this object, but it has such a high speed that it is too fast to fall, so it is constantly influenced by the object, and it falls es fällt vorbei. It passes by, it falls by. It falls around all the time. And this is why satellites moving around the center. So imagine this here is the sun. And here you are moving. And when you move, for instance like this, you will feel not much from the sun. When you start here a little bit closer, then you will feel maybe a little destruction of your old pathway. You will maybe end here. If you start a little bit closer, something like this will happen. If you closer, something like this happens. If you start here, maybe this will happen. Oh, now you are trapped in a kind of an orbit. If you start here, then you are so close that this will happen. And the same happens also when you change your velocity. That means when you are, for instance, here and you are very, very fast, then this is not strong enough to hold you and you will anyway just go away. But when you are very slow, then this will happen. This is actually how the velocity and the proximity influences the dynamics and the pathways. And so, because it's a dynamic system, everything is somehow entangled. And even this ellipse, there you have 1 million solutions depending on the starting point and the starting velocity, and only one spatial pair out of millions and billions of possibilities, only one solution will lead to this stable orbit. And when you are on the stable orbit, then you have this effect. When you're here in this closer area, you will move faster, and here in this further away area, you will move slower. Planet Earth. So, and now there are different possibilities. I think about an object which is moving this line. This object will feel this gravitation, this bigger object, and this bigger object will influence the pathway of this object. When it moves here, for instance, it could happen like, now it feels like, something like this will happen. The slower or the closer to this, it will be influenced a little bit stronger. When it starts here, or when it starts here, but maybe it starts here, but it is much more slower, like this, then it will feel much more about this. And this will happen. And when it's again a little bit slower, or it is a little bit closer, then it will happen something like, for instance, this. And when it's again closer or slower, it will happen something like crash. These are the different possibilities, and it depends on the speed in the beginning and the distance to the object, how far it will come.
How can two dancers, one being the center of gravity, the other one satellite, establish a relation of orbit and sustain it?
The idea is quite similar to this. So one dancer has to be here. And the other dancer is going a pathway, maybe here, quite far away to the other. And when he has the shortest distance, which might be here, then he can think about this dancer, that he somehow influences him, maybe that this pathway is now like this, again, straight line. He can come back or he can start here, because everything is symmetric in this. So maybe he's here, and then he has two possibilities. Okay, one dancer here starts to move in a straight line. When he is in the closest moment to the other dancer, when he has the closest position to the other dancer, then he can think about how he will be influenced if he is attracting this dancer a little bit. And
if
then
he is attracted by the one in the center,
Yes,
you mean, by the
yes,
one standing.
of course, yeah.
Uh-huh.
Then maybe this will happen a short influence like here, and then he will continue his pathway in this direction. And now he can start here.
The same with the straight line.
The same first with a straight line, but then he has two possibilities. First, he is slower, or the other is that he is now closer to this dancer.
So let's do the one that is slower first.
When he is slower but has the same distance, he starts straight like this. He's very slow. This force now can have more influence on his pathway. That's why the influence will be a little bit stronger than here. The same would happen if he starts closer but with the same velocity like here. The dancer here has to think about that closer as well as slower have the same effect about his new pathway after he is influenced by him.
There is for sure some pathway, some equation that says...
Of course. The potential energy, I this is potential energy on planet Earth because this is the gravitational acceleration on Earth, and this is the kinetic energy. E kin is v quadrat. Then I can set them equal. Then I have mgh is like this. Of course, on both sides I can remove the m because it's on both sides, and then this I can everything bring on that side. I mean, it's only the 2 again, 2gh, or I can do the square root, and then I have v is square root of and then you have already some kind information about the velocity. This holds also when you want to describe how fast is a stone when I throw the stone out of a window, blah blah. But it's
Okay.
so now another thing. He starts now much more closer, maybe here, and is a little bit slower. Then he will be influenced much more than here, and this could happen. So now he starts again, a little bit slower, and yeah, a little bit slower, I would say. Then it could be happen like here. Then he's now here, for instance. So you see, he's coming closer and closer. Now I would say he starts here and is coming very close to him. Then this will happen. It feels like a slingshot. Pum. So now, dang, dang, like a. I can show it with your sock. It's a slingshot. A little bit closer or a little bit slower means that this can happen. And now he's constantly falling around this planet. When he is more slow or more close, then he will crash
So
on this guy.
I think I get it. Not to crash on this guy or not to completely pass him by, but to establish a constant ellipse around this guy, you have to find an exact place,
You have to
exact distance from the central guy, and exact
velocity. So it
for
means
your mass and for his mass.
And it means you have an infinity amount of possibilities of velocity and distances, but only one solution for an ellipsoid. The closer you are to the center of the mass, the faster you are, and the farther away, the slower. It's very nice. This is how the Earth moves around the sun. When you are too fast, it could be that you will be farther away from the center of the gravity, and if you are too slow, then maybe you could crash in a spiral on the center of gravity. It could happen. In reality, the small object has also a little bit of gravity, and it will pull a little bit on the heavier object. So actually this will happen a little bit. And the more equal those masses, of course, the more they will influence each other.
We have 2 weights on the ends. Say this way is A.
You said so many things. Let's name the things. This is a bug.
A satellite. And the planet.
The planet.
This is a mass point in space. I put it here. If this mass point experiences a force, it starts to move in a straight line. This is a mass point in space. I put it here. This is a mass point in space. I put it here. When it experiences a force, it moves. It moves in a straight line in direction of the vector of force. When it experiences a force, it moves. It moves in a straight line in direction of the vector of force. Until another force changes its movement. It moves so until another force changes its movement. Your German is hopefully good enough for this. It takes 4 minutes.
Sie heißen Lindemann, richtig. Und dass Sie 500.000 D-Mark im Lotto gewonnen haben und was Sie damit machen wollen, wir probieren das jetzt mal.
Ich heiße Erwin Lindemann, bin Rentner und 66 Jahre. Mit meinem Lottogewinn von 500.000 Mark mache ich erstmal eine Reise nach Island. Dann fahre ich mit meiner Tochter nach Rom und besuche eine Papstaudienz. Und im Herbst eröffne ich dann in Wuppertal eine Herrenboutique. Ich heiße Erwin Lindemann, bin Rentner und 66 Jahre. Mit meinem Lottogewinn von 500.000. Ich heiße Erwin Lindemann, ich bin 500.000 Jahre alt. Nee, falsch. Ich heiße Erwin Lindemann, ich bin Rentner und 66 Jahre. Mit meinem Lottogewinn von 500.000 Mark mache ich erstmal eine Reise nach Island. Dann fahre ich mit meiner Tochter nach Rom und besuche eine Papstaudienz. Und im Herbst eröffne ich dann in Wuppertal eine Herrenboutique. War das so richtig? Ich heiße Erwin Lindemann, bin Rentner, 66 Jahre und ein Lottogewinn von 500.000 Mark. Erstmal mache ich mit meiner Tochter eine Reise nach Wuppertal und eröffne dann in Island eine Herrenboutique. Ich heiße Lindemann und bin seit 66 Jahren Rentner und habe 500.000 Mark gemacht mit meiner Tochter in Wuppertal. Erstmal mache ich mit meiner Tochter. Ich heiße Erwin. Ich heiße Erwin und bin Rentner. Und in 66 Jahren fahre ich nach Island. Und da mache ich einen Gewinn von 500.000 Mark. Und im Herbst eröffnet dann der Papst mit meiner Tochter.
I put in another mass point with more mass. This is a mass point. And I consider it as the center of gravity. Now I put in another mass point with a smaller mass. When the initial velocity equals 0, the smaller mass point will move in direction of the bigger mass point. Like this. When this mass point experiences, mein Name ist Erwin Lottemann, when this smaller mass point receives my force plus the gravitational force of this mass point. This. It adds together to this. When the initial force is quite big, this happens. This means that the original straight line receives only a small influence by this mass point, 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 this point mass point, this mass point, this pass point, this mass 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 point, this point mass, this. Why is it hard? This mass point now receives a bigger image. This is a mass point. I put it in space. This is another mass point. When this mass point receives the initial force, when this mass point initial force, which is quite high, it will only be influenced by this mass point like this. A hyperbola. Hyperbola. When this mass point receives a quite small initial force, this will happen. A spiral. This is a kind of a hyperbola. Hyperbola. When this happens, I have something like a parabola. You know it from mathematics in school when you have this parabola with x. Blah, blah, blah. So, and then I have an ellipsoid, or I have a spiral.
And these are the options?
These are the options.
A spiral. A spiral. Spiral.
Can you explain what is the relation between the bigger mass point and the smaller mass point so the ellipsoid comes to be?
A parabola can also happen like this.
And hyperbola?
And hyperbola is like this. I want to throw this to the trash can. When I use too much force, if I use not enough force, I need a certain amount for this distance. And the same is with the initial force. You have to calculate with this mass point, with the center of gravity, calculate how big the initial force for this mass point has to be. It's a very easy formula. Centripetal force equals the gravitational force. In school, usually we learn this when we are teenagers. You are now running on reserve battery power. You need to plug the power adapter into, or everything will be erased. 10, 9, 8, 7, 6, 5, 5, 5, 5. I close the windows when I go pee. After a while, the both mass points start to move slowly, but ignore your satellite. You are so heavy and so strong, and the satellite is so tiny and so light, you can walk, and the satellite has to follow you. When the both centers of gravity come too close to each other, they also will influence their movements. Peanut shape form instead of a circle. Peanut shape. Mass points with the same mass, and now you can try to orbit around each other. You have the same mass, and think of it. If you are close to each other, you are very fast. If you're far away, you are more slow. And think about all these forms: hyperbolas, parabolas, ellipsoids, spirals, crashes.
actually.
With the two stars in the center, not just one.
I know, you have to describe quite often use double stars and triple stars, and then of course the planets have more complex.
Oh wow, and they
The two stars come too close, then the planet could fall into the sun or just accelerated far away.
we all know this moving through the space, blah 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 blah. And this was just another version of it, but still it gave some nice dynamic to it.
Modern physics is the 18th and 19th century, the northern hemisphere. In Europe, in North America, and Russia, China. And the models from this time where they had now the idea of ensembles, that means moving of really a lot of particles. They used statistical methods, and now they had the idea of a field of forces. Not only an arrow, but there's a field. The thinkers of gravity were Leibniz, Boltzmann, Lorentz. Context lots of new laws in physics and unification of theories. Classical physics was completed.
So we can have peanut butter and Leibniz.
Okay, now we come to more contemporary part of the physics. The dramatic changes after 1900, the northern hemisphere, from 1900 to 1920, and the models in this time, four-dimensional Minkowski space-time. That means time and space are gleichberechtigt.
Equal.
They are not separated anymore. Time is another dimension, like this dimension, that dimension. We have four. And the speed of light is fixed. And this changed a lot how to describe movements.
But actually it's still not equal because it's three times space, but only one time.
But in
It's
the
dimensions.
the dimensions are equal. When you describe them, we have a mathematical model and then we treat them as equal. The special relativity was born. And with this theory, there was no center of the world anymore. It was a picture of the world where there's no center. Everything is equal to each other. Inertial systems are relative to each other. That's why it's called relativity theory. A couple of years later, the general relativity theory was developed. It was about the structure of the space-time. The most important sentence is matter curves the space-time, and the curved space-time tells the matter how to move. Matter curves the space-time, and the curved space-time tells the matter how to move. Materia curves the space-time. Like I have a heavy ball and put it on a rubber tissue, and it's curved. And now it has a different shape. And this different shape causes different movement of the matter. And one very interesting outcome is the concept of the black holes. It means there's a point of an infinity curvature of the space-time, where it goes to infinity. It's called singularities. Look how he changes the space-time structure. Whoa, it's bent. It's not flat anymore. Woohoo! Ivan, but you are not a black hole, you're not fat enough. And the event horizon of the black holes, that means the corner where no light is coming out anymore, the time and the space can exchange their roles. That means that you are able to move time-wise, but not space-time. Event horizon. What is happening?
Event horizon.
The event horizon is the place. From here, the light will not come out again. This is called the event horizon. And
Such a nice title for something that's actually quite scary. Like that the light will never come out of it again. It's very full of doom.
the light is doing, nothing happens to the light, but from this border, it's just the gravity is bending the space-time so much that the light will not be able to come out. Some of the thinkers were Einstein, Planck, Friedman, Hubble, and the context, they found at the same time the quantization of objects and energy. And both Einstein theory and the quantization, of course, changed how we see the world. And I think it's still until today that not everyone gets this idea of how the world was described, and this is already 100 years old. But for this, I give you now a very nice exercise, very thrilling. When you start to move through the space and the time here in the room, and try to be not so complicated, otherwise you will freak out in a minute. So just start to move and observe yourself and the others, how you use the space and how you use the time.
I got a little bit lost. Yeah, and for me it was like, okay, I jumped to the side, so it was something in space, but then it was also and in my perception it was quite connected because it was a fast change to the sides, and then head. So yeah, how can I change it now? Like,
You use the 3 dimensions in space. What does it mean to time? How to project it to 1 dimension?
Is it really like this, that time is just 1 dimension?
The time we experience is just 1 dimensional, but I mean there are concepts of more, but the one we experience, this is just from the past to the future. There are other cultures with other ideas. For instance, the Aborigines, they have the now time and the dream time. Now we come to the more dramatic changes after 1920. The physics were developed all over the world. The main models were now about the quantization, about the fields in the 4-dimensional space and time, and even the space-time itself become quantized. The English word is also Ansatz. The Ansatz for the theories is Ansatz. Yeah, they use the German term in the international use.
A lot of things like that.
Yeah, because the physics in the 19th century were quite strong, influenced by the German, as well as of German words come into this. Quantum loop theory, the string theory, the theory about area metrics, and it included ideas like that the space-time is quantized, that means it is discontinuous. So you can imagine the world as foam, Schaum, and the world exists only where then the liquid is, and in between, in the bubbles, there is no world, there's nothing. The space-time was now not anymore like before, like this room where things are inside, but the space-time or the vacuum is already a thing, like the paper. When I paint a picture to a curtain, then of course the curtain is already a thing, and not something empty. The curtain is something I can hold in my hand, and the same is with the vacuum. The vacuum has a structure, and the vacuum has a very high energy level. And it makes it very interesting, even if we think about the foam, what the vacuum has a structure, like this. Only where my fingers are is space-time, in between not. There's another model, holographic universe. It means you have a 3-dimensional picture and it is projected to a 2-dimensional surface. So that means we are some kind of projections of a real world we are not able to see. It's nice. So you see where we go now. Some of the thinkers in this world were Schrödinger, Dirac, Heisenberg, Bohr, Fermi, Feynman, Young, Lewis, Stringer,
hundreds more, because there were a lot of physicists now. And of course the knowledge about the world exploded in the 20th century, because so many new fields developed, the whole stuff influenced each other. And yeah, and now I have a very nice last exercise. Move the bend and move, float in space-time.
So what are we doing?
Now you move through the space, which is bend and moved.
Bend.
A bend space-time, like. And it's floating, the structure. It's not rigid, it's just another space-time.
Willst du bisschen auch mention this membranes? No, this theory.
Yes. This is the idea in the string theory. Yeah. This is one very special idea, but there are so many other theories. What are the membranes?
Foam exercise.
Foam exercise. What was it about? Okay. Yeah, take a spot in the space, wherever you want, and you can slowly start to move through the curved space-time structure, as you did it in the exercise before. And now think about that space-time is not continuously. So you can, for instance, start to put both hands on your stomach.
Sind die gewaschen?
Nee. Aber Bio.
certain areas where you have space-time, but you you have to find a movement into this curve and then space-time where you can't say places because there are no places in between, which is not continuous.
Nee. Aber Bio.
So, imagine you are in the curved in space-time. And you move somehow in this curved in space-time. And imagine that space-time is not continuously like this side, but it's more quantized. So you have certain areas where you have space-time, but you have also certain areas where there's no space-time. And you have to find a movement into this curved and bent space-time where you can't say places because there are no places in between, which is not continuous.
So, Sebastian, can you please explain me the form exercise?
So, we have still like an Einstein, the band in curved space-time, but it's not smooth anymore, it's more like this t-shirt. From here it looks for you quite smooth. But when you come closer, please come closer and closer and closer and closer, you see a structure. And here you have kind of holes or places where the t-shirt knot is in between. It's very clear. So there's a structure. That means the t-shirt is not continuously, it's not smooth. Like the space-time. Space-time is not smooth, it's not continuously. There are places in between where space-time not exists. And you can think about it like foam in your bath, where you have only, where here the t-shirt is, there is the liquid, and in between are some bubbles with nothing, or something else we don't understand. So you are now the third person who want to do the foam exercise. Very good. Nobody's doing something else.
No, but the rest is already filmed. So I just looked. I watched the film. So that's why I'm just missing the foam exercise. That's my problem.
The task is very simple. I mean, imagine the curved in space-time. We have it Albert Einstein. So you move in this space-time, and it's not smooth like this. It's like when you go very close to my jacket, and you see there's a structure. It's not smooth anymore. So you have small spaces in between where there's no jacket, there's something like air. So it's not continuously. And the same holds for the space-time. So when you go to the studio, move in the curved space-time, and think about the discontinuity?
Discontinuity?
Yeah, the discontinuity of the space-time.
Okay.
Have fun.
So I imagine a curved space-time.
So there's already something happening to the space-time.
And I think about the now when you have to... Ja, Englisch. Ich. Okay.
Look at this.
Ooh.
It's for free.
And that's all. That's the whole exercise.
That's the whole exercise, and what you do with it, with this, it's.
Yeah, but I don't do the exercise actually.
You lucky one.
Yeah.
Scroll. You are my touch
screen.
screen.
So
Help me.
we're in
help
part
me.
2 now.
What I explain now is the kind of quantum physics, and there are some exotic things happen, and then later come quantum field theories, and due to this quantum field theories, that the curved and bent space-time is not continuously anymore. And then I like to explain people like, look at this nice t-shirt. From far away it looks like it's very smooth, but when you look with microscope, you see that it's just air, because there is a web of tissue, it's a web, and in between is nothing. And this is how the universe or the space-time is actually organized. It's just here, but not in between. Of course, the structure is more complicated, blah blah blah, strings or not, and quantum groups, blah, but we don't care about this too much.
So it's a t-shirt theory.
So it's a string t-shirt theory.
Yeah, but the string theory is just one theory. You have different theories, and the string theory is not very liked in Europe. It's more from the United States. In Europe, they believe more in quantum theory. But the idea is the space-time is physics and belief. So we have curved and bent space-time, but discontinuously, even the time. So the time is really like tuck, 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 and not like in the same as with space, but space-time, right? Yeah, but did you do the right, or if I'm an observer sitting inside, for me everything looks smooth because I'm not able to see this. But from the outside observer, it looks like you have these curtains, you know what you can jalousie. Here. Yeah, you have a jalousie, and then you have a picture on it, and then maybe you have a video beamer and put a movie on this jalousie, and then. For the guy in the movie, it was continuously, but for you, of course not.
The absent, or can we describe it as negative space?
It's a good question. What is negative space? Imagine time and space is discontinuous.
Rupture?
Well, in body terms, that would be about breaking movement and then reinitiating somewhere else. It would be about relative stillness and then reinitiation, so that you're not working through consecutive flow, going to this to this to this to, and fragmenting certain properties potentially, but not every level.
Okay.
So yeah. It would be. I would interpret this as reinitiations, implying flow and floating, so now you can really make a balance of fragmentary phases. This is about initiation phase.
I think nobody of the teachers there will have an idea about physics. I mean, most of the dancers are quite esoteric. This is energy in my spine is connected to my aura, and the relay is. I hear this so often from these teachers, and I think, okay, you have an aura. So, I'm so mean when I'm tired.
I quite like it though, because like the filter button comes up. And
then
it's just like, it happens to me when I'm really tired, and it's quite fun.
Yeah, I mean it's good to be honest sometimes, because I'm not really mean about it. It's just unclear about it.
I think sometimes the esoteric language in teaching dance can be like deliberate images to create a particular quality, and that's really helpful.
Yeah,
and sometimes it just becomes kind of hilarious, and people sound a bit stupid.
Especially when teachers say, yeah, Sebastian, you're a physicist, you know about the aura. Yeah, I know that there is no aura. And this is actually not, this is actually still part of the exercise before, but this I give them only to adjust already, to arrive in this space-time.
Yeah.
And then they have a closer look and they say, ooh, it's not smooth. There are holes.
Look, also in the lines. Yes.
It's like here. Come very close to my t-shirt. Closer and closer and closer, and you see this nice structure and the holes. Not smooth.
A funny part of it is closer I am, less light it is, so less I see.
Yeah, because the wavelength of the light is only 500 nanometers. I use the term from physicists. They call it sometimes foam, space-time foam.
Okay.
And that's why some of us call this the foam lecture.
Right.
Just that you know when this word pops up, what it means. The foam is, it's the same like this, but just round.
Yeah.
Three-dimensional.
Yeah, which is interesting because it does create the image of something very airy. And if I try to move foam, do you know what I mean? Like, this happens. Like, the image of foam does something really different to the idea of dots and spaces. I like dancing your work. It's nice. It's very confusing.
Can you say when this is here the foam and this is inside? Is this a bubble in the foam? Is inside of the bubble is there foam or is this not foam? It's a good.
I do like
theoretical.
feeling last year, but I'm angry at you.
Am I looking at it?
Last year I was also angry at you.
It's a great thing.
Yeah, of course it's repeating.
Am I looking at with the space inside that? And then going, there's no foam.
Yeah, I feel left alone because I felt like I was running like for this shitty days and nobody was helping me, and that you even wanted to kind of, you know, like change like stupid stuff.
I just need a little bit more help with the
You know, making a bit more space there, and that I even had to argue for not doing stupid work, you know, and then I was late, I could not prepare, I could not watch Maya.
There are foam lectures. They not foam lectures, but they call this model. It looks like foam.
And also peanut butter, you came and were disturbing me, and I ran for the laptop and I ran back and forth and back, and then you didn't even use it and you didn't even close it, and also the Zoom, I don't know where it is, and it's like I feel like I run and I do things for you, and okay, you don't even say thank you in the moment, and then also it would have been so much better when you would have spent more time with us working on the movement, like what we do, like spending more time on the people, like actually on the human beings that are there, on the bodies, and not on all this shitty virtual stuff, you know, it's all virtual, and then because the bodies, like, we don't know what we do, so people are bored and actually watch this virtual stuff. But when you would have worked on us and with us, you would be better, and everybody would like to watch us, and then it would have.
And this is a very known picture from the quantum loop theoreticists, how they describe it. It's color coded, every color means something.
Yeah.
And yeah. So.
Okay, cool. Thank you.
I try to do and follow, but I'm not an acrobat. For me it's quite complicated to lift immediately some with this and do this and that.
Yeah. Was it fun though? Was it fun though?
For the others, yes.
But for you, not so fun?
Not today.
Okay.
Because I was so tired.
Oh, well done for getting through it.
But I will learn. And now I have to do some other stuff, but then I'm allowed to sleep.
Indeed, indeed.
But this night is not that hot like last night. Yeah, sorry that I'm in this kind of strange mood, but...
Oh, just go. Bye.
Bye.
Space time.
Thank you so much, Space Time. Travel well, sleep
You
well.
follow me to the street with this?
Maybe from the other side.
The balcony. So...
Thanks, man.
Yes, you're welcome. Ciao.
Ciao. Have a good one.
Bye. I'm going to eat some nougat bites.